Come? Ah.
Okay, so let's just carry on while you receive the notes, which are great because it means I can maybe write a bit less on the board and just point you to various things. So now we're just once again considering the displacements of rapidities of the ground state after having added a variable on the right hand side of the Fermi sea. These little dj's characterize the displacement of the rapidity that was associated to the quantum number associated with ij. And these dj's are of order of 1. Okay. So here we're just doing some manipulations. Actually, the manipulations that you have are relatively straightforward. So let me just point to equations, 1.94, 1.95 in the notes. So essentially, what you do is that you just stare at that long enough. You replace the summations here in terms of integrals involving the densities rho of k that we have, which are densities just for the ground state. Okay, and then you see what you get. So essentially, you get such an equation here. Let me not write its continuum form, which is just equation 1.95 in the notes. It's really just taking this and substituting the densities that we have, transforming them into integrals. Okay, so let's just instead go one step further. So we introduce a function which I'll write as d for displacement, which contains 2 arguments. Okay, so this is the displacement of the rapidity that sat at k by the addition of an extra particle at q. Okay, so this is really just this function that we had. So this, maybe a couple of steps. So dj here is the displacement of the rapidity associated to j. But I can just view this again, same thing as with the densities. I view this as a continuous function of k. But of course it's dependent on q. So really you can just view dj. dj becomes a function of 2 variables, d of k and q. Okay, but it turns out that in this equation here, there is naturally the appearance of this factor here, okay, which, if you just invoke the lead equation, just becomes the density rho k. Okay, so that's why you essentially just, or the inverse of that here. So if you just define this displacement d of q as this little dkq that we have, times the rho of k, you get a clean looking equation for this displacement, and this clean looking equation is like this. So it has essentially a shape that I'll comment on a little bit. dkq minus integral minus kf to kf dk prime of this Cauchy kernel we had, k minus k prime, okay, and then d of k prime q is equal to minus 1 over 2 pi times pi plus phi of k minus q. Okay, and here the q that we had, really we're doing it for q greater than kf. So q is the particle rapidity. It's somewhere outside of the Fermi sea on the right hand side, so we have this. Okay, now just a couple of comments. You remember the Lieb equation? The Lieb equation was of the form rho minus with this Cauchy kernel times rho is equal to driving term being simply 1 over 2 pi. Okay? Here we have the same left-hand side, but a different driving term. Okay? So there are many equations in thermodynamic beta ansatz that look like this. Always the same integral kernel applied to a function is equal to a different driving kernel. Okay, so once you start learning the monkey tricks to deal with one of these equations, typically you can do with all of them. You can deal with all of them. Okay, so this is essentially the equation giving you the displacement of the rapidities once you add things. Now what's that good for? Well, of course you can now calculate the energy and the momentum that you've pumped into the system by adding this particle. Okay, so the momentum in a sense we kind of already know, right? Because we have the quantum numbers, so we had specified it, but that's because we knew it in terms of the quantum numbers. In terms of Q, this little Q here, we don't know it because we haven't solved the beta equations. So here we view it the other way. We view Q as the input parameter. Okay? We say we add a rapidity Q, but since a rapidity is not a momentum, Q is not the physical momentum you've pumped into the system. So you need to calculate the momentum you've pumped into your system. Okay, so what is that? So the change in momentum you can just calculate by taking the difference, once again, between the solutions of the beta equations for the excited state minus those of the ground state. You remember that the total momentum of the system is just the summation over all rapidities in that state. Okay, so we do this, momentum of excited minus momentum of ground state, so we just have this Q parameter, and then plus the summation 1 to n of just kj minus kj0. Okay, so this we can just rewrite as Q plus going to the thermodynamic limit, it's the integral from minus kf to kf dk of simply the displacement kq. Okay, so that's the momentum you've pumped into the system. So once again, you give me Q, I calculate d of kq by solving the integral equation. Once again, as for the case of the lead equation, the solution of this integral equation it exists, it's unique, fine. So you can find it, and then once you've found the d, you calculate the momentum you've pumped into the system, and you can also calculate the energy that you've pumped into the system simply by, so the delta E. Okay, so this is just Q squared. You can put, if you want, I do it in the notes, minus mu, because here there's a chemical, you imagine that you're working in a ground canonical ensemble, there's a chemical potential, so you got a particle, you see this. Okay. And then what you do is the summation of k squared minus k0 squared. Okay, again, the difference between the two is small, so you differentiate the k squared, you think 2k. So the change in energy is just the integral minus kf to kf dk of k times d of kq. Okay? And similarly, for the nth conserved charge, the change would be q to the n minus the chemical potential of that charge plus simply n times integral of k to the n minus 1 d of k. Okay? Simple as that. Okay, so now this is essentially the way you calculate basic properties of this. Of course, your understanding of what you're doing is reliant upon solving for the displacement, solving the integral equation for the displacement. So there's essentially, so two simple limits. You can do it. So simple limits. Did you need to write anything? Okay. So two simple limits. If you take c to 0, then what you find is that the displacement here is just 0. You have no interactions between your particles, so the displacement is 0. And essentially, what you obtain is that the dispersion relation, so the energy you've pumped in for a given momentum is just p squared. Okay, so you've got free particles, which is great. you hadn't found that, there would have been a serious problem. More interestingly, if you look at C going to infinity, then the solution for D, you can work it out, it becomes -1/2. And then you can just work it out, and the dispersion relation that you obtain by simple algebra is something that looks very much like something you've seen before, P plus 2 pi NP. Okay, and this is for C going to infinity. Okay, so you see essentially that when you go to the Tongt-Giraudoux limit, you kind of recover some Bogolyubov type dispersion relation for your excitations. Okay, so I mean it's not exactly the Bogolyubov square root, but its two leading terms coincide with the Bogolyubov approximation. Okay, so non-interacting particles, free dynamics, energy is p squared. Infinitely interacting particles, still, free dynamics, p squared, but it costs you the energy of displacing the whole C by one little step. Okay, so it's proportional to the density and the momentum that you have. Okay, so these are two simple limits. So this is for the type 1 particles. So type 1 particles, essentially you can think of as the glorification of the Bogolyubov modes for the 1D Bose-gas. Okay? Now there's another set of excitations that we can construct. These are the hole-like excitations. And, no surprise here, type 2. Write it in Latin letters so it looks more serious. Type 2. So in this case here, I guess it's extremely similar. Maybe what I can even do is skip this because you have it in the notes. So let me actually do that for kind of optimization's sake. So what's a type 2 excitation? Now you start with the ground state with n particles and you drill a hole somewhere. So you remove one of the particles and then the others of course have to go to the other half integer lattice, and this hole is also a bona fide excitation. It has a label that has to live between -kf and kf in terms of rapidity. And it will induce also a reorganization of all the other rapidities in your state, following exactly the same procedure with trivial modifications. You can also recover a displacement function associated to this hole. Right? You can calculate the momentum and the energy that you've pumped into your system when you've created this hole as well. So this you will find in the notes. Okay, one interesting comment is, of course, that within Bogolyubov theory, there is no correspondence for this excitation. This excitation has a correspondence in fermionic systems, because in a filled Fermi C, of course, you can drill a hole, and then you know that holes propagate. Right? That's the fun thing about fermions. If you have fermions on a lattice, and you remove one fermion, it creates a hole, and then it's much better to forget about your fermions, but you view your hole as the important excitation. Okay, so here it's exactly the same thing. So the hole becomes its own dynamical excitation. Okay, so the finicky among you might raise their hands in protest, saying, you are double counting, you are cheating us, because, haha, I can create your whole excitation, okay, by simply considering a state with 2 less particles and creating a macroscopic number of type 1 excitations, right? So a state with a given hole somewhere is just a state with 2 particles less, 1 particle added, and then, just adding all the things, leaving 1 hole behind, okay? So, are we double counting? Yes, we are double counting, okay? But why is it smart to double count here? Because we don't want to create excitations by essentially having to reorganize a macroscopic number of quantum numbers. So it's much more efficient to essentially identify the excitations created by the hole, not as a macroscopic product of type 1 excitations, but as a single creation of a type 2 excitation. Okay, but then when you calculate thermodynamics and things like that, you would have to make sure that you don't do double counting. But that, you know, never happens. Because essentially what you, well, at least when you're considering low energy subspaces in your Hilbert space, you don't have to worry about that, because the operation of, you know, creating a macroscopic number of type 1, you're not going to write down in your trace. Okay, but anyway, so that's a little subtlety that you might want to keep in mind. So I think it's if you quenches and things like that, you might be cheated by your calculation if you don't do that right. Anyway, so then you'll have policemen like me phoning you out. Okay, so what I would essentially like to say here is that this concludes the investigation of at least the vicinity of the ground state. So we now have an explicit expression for our ground state in the sense that we have an explicit equation, an explicit condition for the distribution of the ground state, the Lieb equation, the Love equation. And we are able to construct essentially a denumerable set of excitations around the ground state. And the nice thing about these excitations here is that the contribution of many, you know, a denumerable number of type 1 and type 2 excitations to the energy, to the momentum, to the particle number, it's additive. Okay, so we have strongly interacting bosons, but the type 1 excitations do not interact with each other. Type 1 and type 2 are free excitations, up to corrections of order 1 over L. So you create 1,000 type 1 excitations, the energy you've pumped into your system in the thermodynamic limit is the summation of the expression that we wrote down over the 1,000 things. There's no nonlinear term in the talking between these excitations. It's a very important fact. Of course, it's only true to leading order and 1 over L. Okay? Otherwise, of course, they still count. But you don't need to worry about that. Okay, so it gives you a basis, essentially, so the language of the type 1 and type 2 excitations gives you, if you want, like ladder operators to explore the whole Hilbert space at a finite energy above the ground state in the thermodynamic limit. So then you can do finite temperature thermodynamics with that. Well, not really, actually. No. To do that, we have to come to the next subject. Okay, but you can at least do all the you know, response functions for normal physical operators around the ground state. You can already understand those in terms of creating type 1 and type 2 excitations. I'm not going further than that. Okay? So let me then start. I mean, are there questions about this? Is that kind of clear? Okay? So. With the wine of vino rosso tonight, we'll all fall into this. No. Okay, so I now want to move to the next big subject. I'm not quite sure. I guess we'll be able to do quite a bit of it. I want to talk about thermodynamics. Now, when I say thermo, I mean it. Okay, I want to talk about equilibrium thermodynamics. Okay, the way we do equilibrium thermodynamics, of course, is by using the language of Josiah Willard. We compute partition functions. We put external levers onto this. We will talk about a temperature. We will talk about a chemical potential. Okay? And we will essentially compute a partition function that will be the generator of all equilibrium properties of our system. So we want to compute a partition function. Okay? So we want to have some z, which will be a trace of e to the minus, you know, e minus chemical potential n divided by t. Okay? Boltzmann's constant is 1. Now what we know is that, well, at least what I've drummed into you is that the set of eigenstates that we have, the beta wave functions, form a complete set of states. So we can just compute this partition function by explicitly summing over all eigenstates that we have. And for each eigenstate, we don't need to deal with the beta wave function. We just need to know its energy. Its energy, it's simple, it's the sum of the kj squared. So we can calculate this thing. And the way we calculate it is that we say, okay, what we do is that we do a summation over particle numbers. This can go from 0 to infinity. Then at each fixed particle number, we do a summation over all proper sets of quantum numbers with this cardinality n. And then we just calculate, you know, e to the minus, then the energy of this state, minus mu n over t. And the job is done. Okay? So that's great. And that's indeed what we're going to do. Now, of course, such explicit summations here cannot be performed in closed form. So the first simplification, or the first kind of road that gives you hope to calculate these things, is to go to the thermodynamic limit. Okay? When we go to the thermodynamic limit, essentially, we've seen that we label our eigenstates in terms of distributions. So first of all, sets of eigenstates we can write in terms of densities rho of x. Okay? And then essentially the statement is that give me any rho of x that is bounded between 0 and 1 for all x, and I will give you one eigenstate that has that. And fine. So you rewrite the partition function here as a functional integral over the functional labeling of the eigenstates that you have. Okay, so let me just write this. So essentially what we expect is that z in the thermodynamic limit would be given by some functional integral d. Then the question, d what? Well, okay, so the rho of x, the quantum numbers are statistically independent. Okay, so in the sense that you can sum over these sets of quantum numbers, the Jacobian there's no Jacobian, the measure is just completely flat in the space of the quantum numbers. Right? Now, we don't really like working with our rho of x, we like working with our rho of k. Okay, so then there's a mapping between the two that comes from the beta equations, but that's fine. Essentially what you can do is write the functional integral as a functional integral over rho, and, well, let me write rho of k, rho whole of k. Okay? Modulo the beta equations. Okay? Because, of course, that's a relationship between the rho and the rho whole. Okay? And now, of course, so there's the energy of this state here that will appear in there. So there's going to be minus e minus mu n over t, okay, where this e is just the energy or the number corresponding to the rho that you give me. But of course, there's one subtlety here, because when we provide a rho of k, or a rho of x for that matter, and we go to the thermodynamic limit, we are bunching together an extensive number of states that look just the same. Okay, so if I take the thermodynamic limit and I have my set of quantum numbers here, and you know, we say that we go for smooth things, well, actually it won't matter to me very much whether you put one of the quantum numbers here or there. Okay? So there's going to be a lot of opportunity for shuffling the particle and whole quantum numbers within little windows that are so small that you don't care about. Okay? Because all these windows are of order width, you know, of order 1 over L, or some subleading thing. Maybe they're of width 1 over square root of L, which is much larger than 1 over L, but still you don't care about it when you take the thermodynamic limit. Okay? So there is an entropy function appearing here, an entropy functional, e to the s of rho, that appears here. And this entropy functional is known as the yang-yang entropy, because yang and yang are the ones who, for the first time, did thermodynamics of integrable models according to this language here. Okay? So what is this entropy? Well, the energy we've seen, right? It's just integral k squared rho of k. Particle number is just integral of rho of k. Okay. But what is this entropy? Well, actually, what you can consider is an interval. Between k and k plus delta k, okay, where this delta k is much larger than 1 over L, but is still much smaller than 1. Okay? So in such an interval of width delta k, there will be L times rho, well, just look at this, rho of k, delta k particles. There will be L rho whole of k, delta k holes, okay, in L rho total k delta k slots. Okay, so a given delta k represents a certain number of available quantum numbers which are either busy or free. Okay? And now the statement is that as far as the thermodynamic properties are concerned, okay, and I emphasize this is not true for many things. For example, if you wanted to compute correlation functions here, this is a thing where people have stumbled in the past. It's not true if you do things like correlation functions. But if you do things like equilibrium thermodynamics, then you can pack together all states that are only related to each other by permutations within these boxes delta k. Because they have an energy which in the thermodynamic limit is identical. They have a momentum which is identical. They have a particle number which is identical. They have all conserved charges, and you can measure up to a number which is less than system size. You know, a few 10,000, the higher charge will have an identical eigenvalue. Okay, so you cannot distinguish them in the equilibrium properties of the system. So you pack them together. Right? But then it's just a fugacity, right? So you just count the number of states that there are in this box. Now you can easily do that because this is simply, you know, this choose this, right? So the total number, so the number of states described by rho of k in the thermodynamic limit. Let me, well, maybe I can, I can just write straight the answer. Okay, so given a certain rho of k, for each interval delta k, there are certain numbers of states that you count by just counting the number of permutations within this box that you are allowed. So the total number of states that differ by permutations in k plus delta k. Okay, so this thing is just equal to this ratio of L rho plus rho whole delta k factorial, right, divided by L rho delta k factorial and L rho whole delta k factorial. Okay, so then you do the standard trick. You invoke Stirling's approximation. Log of n factorial is n log n minus n. And you forget about the root 2 pi jump that comes afterwards. You don't need it for this. So you can obtain the yang-yang entropy, okay, which is S given the configuration rho and rho hole is equal to an extensive quantity integral from minus infinity to infinity dk, and then so you just need to do the Stirling approximation, cancel a few things in there, so all the logs n, the l's, they cancel out, okay. And then it just leaves you with this, so rho plus rho whole times log of rho plus rho whole minus rho log rho minus rho whole log rho whole. Okay, so this is essentially the entropy of the state that is labeled by rho of k. It makes sense because if you imagine, for example, that your state is, well, you know, so if rho or rho whole becomes 0, then there's no contribution to the entropy in that region. Okay, that you just see from this. And the most entropic state you can think of is precisely a state where you have more or less an equal number of particles and holes, because then the number of permutations that you have is maximal. Okay, so a high temperature state, you would essentially get precisely that, right? So you would just uniformize the distribution of particles and holes, at least in regions of K where you find your particles. Okay, that's how you find it. Okay, so this is our entropy for the states. So now essentially what we have is a functional integral for the partition function. So our z here we can write as a functional integral over these, you know, so maybe let me write it like this. Okay, e to some functional g of rho whole. Okay, and here modulo the beta equations, where this Gibbs free energy here is given by, you know, a kind of long thing. It's an extensive thing. Again, you have the integral from minus infinity to infinity dk, and then there are contributions from just the energy. All right. Okay. So there's a rho of k that appears here, and now we have the energy, which is k squared, the chemical potential with the particle number, but the particle number is just integral of rho, so the chemical potential comes here. Okay. And then you have some other junk that comes from the yang-yang entropy. T log of rho plus rho whole plus T log of rho. So that goes into this parenthesis here. And then there's a plus rho whole. Okay. And then you have minus T log of rho plus rho whole plus T log of rho whole. Okay, and this is like this. Okay, so we now have an explicit expression for the Gibbs free energy given a rho and rho whole. So essentially, the way we do the calculation is that we let rho and rho whole vary, and then we will try to evaluate this in a saddle point approximation. Okay? The reason why we are entitled to make a saddle point approximation here is because the system size gives us, if you want, the small parameter, right? So the large parameter that just kills the fluctuations. Okay? So saddle point evaluation. So we consider variations. Rho of k goes into rho of k plus delta rho of k. And the same thing with the rho whole. Goes into rho of k plus delta rho whole of k. Well, yeah, time is flowing, so let's see. It's let me just skip equation 1.118, which is really just doing the functional differentiation. I presume you're all on friendly terms with functional differentiation. Okay? So you can write the variation of the Gibbs free energy in this way. You get equation 118, which simplifies to something relatively simple. So you get that the variation of the Gibbs free energy you can write as the following thing. Okay, then there are two contributions. There's a delta rho of k times the k squared minus mu minus t log of 1 plus rho whole over rho. Yes. Plus a delta rho whole times just minus t log of 1 plus rho over rho whole. Okay, we have considered that the variations delta rho and delta rho whole are functionally independent. But this is not the case, of course. Right? So delta rho and delta rho whole are related by the beta equations. Okay, so if you just look at your beta equations in the continuum formulation, in the thermodynamic formulation, you'll find that delta rho of k minus c star delta rho of k is equal to minus delta rho whole of k. Okay, so the idea here is that we've done the saddle point evaluation in an extended space where both rho and rho whole are free to vary, but we thereafter take the slice where these variations are linked to each other. So we get to the same saddle point. Okay, so just substituting this in the form of this here, you get a nice expression for this variation, which is just a single integral that now is rewritten exclusively in terms of delta rho of k times a big parenthesis. So k squared minus mu, okay, minus t log of rho whole over rho minus c star t log of 1 plus rho over rho whole. Okay, so what's the magic of the saddle point approximation? The magic of the saddle point approximation is that it gives you a functional relation when you take it. The idea is that if you are sitting at the minimum of the effective action given to you by the Gibbs free energy, then this has to be a stationary point. Therefore, for any variation delta rho, the change in the Gibbs free energy has to vanish. Therefore, the expression in curly brackets here vanishes at the equilibrium point. Okay? So the saddle point condition is that this thing is equal to 0, okay, for any k. Okay? So you see, we had the beta equations that were relating rho and rho whole, but we still had one functional degree of freedom. Now, the condition of thermal equilibrium in the saddle point evaluation here gives us a second functional relationship between rho and rho whole. Therefore, if all goes well, we have no more degree of freedom. And we find an explicit solution for the state describing the thermal equilibrium. Okay, that's the idea. Is that okay? So let's just look at this condition. So one of the things that we do is that we define a useful notation. We define a new function which we will write as epsilon of k, which is so it's not the same epsilon as earlier. When we were doing the evaluation of the displacement and things, but you'll see it's very much related. We say that this epsilon of k is t times the log of rho whole over rho. Okay? So that allows us to just rewrite this thing in a more simple fashion, because you see here it's just e to the minus epsilon over t, and here you'll just get some epsilon. So the saddle point condition becomes a single equation, which is that this function epsilon of k is equal to k squared minus mu minus c star t log of 1 plus e to the minus epsilon of k over t. Okay? So now it's a single functional equation for a single function. Of course, this is a complicated integral equation, much more complicated than the Lieb equation that we've seen, because it is extremely highly nonlinear. The logarithm in there is a particular pain in the what's it. Okay, so in order to find explicit solutions to this, it's very, very difficult. Okay. Now, if you work a little bit, so the free energy itself okay, so it's just a tiny bit of algebra to show this. So essentially the Gibbs free energy itself becomes, let me just write the important formula. So the Gibbs free energy density per unit length is equal to this nice looking expression. Okay, with just, well, the t I've already written, so log of 1 plus e to the minus epsilon of k over t. Okay, so this is it's a nice thing because there's a very nice cancellation between loads of complicated terms that occurs, and what it gives you is an expression for the free energy which is dangerously reminiscent of expressions you will have seen for free energies of fermionic systems. Okay? It's exactly of a fermionic form, because for fermions, if you have a given mode, there are two possibilities, unoccupied or occupied. If it's unoccupied, you count 0, so that gives you 1. If it's occupied, you give 1 cost of the energy, which is this. Okay? So this is like a fermionic Gibbs free energy, except that you are not free to choose the one body energies epsilon of k as you wish. These epsilons of k are determined for all k once you have set the chemical potential and the temperature by the equilibrium condition here. Okay? So you determine the, well, you fix the interaction, of course, first. You have the chemical potential now, which enters here. And of course, chemical potential is Legendre dual to the filling. Okay, so now chemical potential has taken the place of your particle number. Chemical potential is important. Temperature sets the mean energy. Okay, so it's a completely closed form formulation of the thermodynamics of the molecule that we obtained. Okay, so these are the two important equations. So this one here being the condition of thermal equilibrium, and then the free energy itself being given by this one here, which is also very important. Okay? Now, those of you who really want to know absolutely everything about this, then you say, yeah, but what about the rho of k? How do I recover the rho of k? Well, okay, in order to do that, you just have to go back to your other equation, your beta equations, and if you know the epsilon, you can calculate the rho of k. You can also calculate the rho whole of k. Okay, and that's the way you can figure out the filling of things. So I could show you some other equations that allow to do this efficiently, but I'd rather just leave that for now and just discuss two simple limits. So simple limits. So when you take c goes to infinity, the so-called Tonchiado limit, then the nice thing is that, as we've seen before, this kernel c just vanishes, so the epsilon of k just becomes k squared minus mu. Okay? So now this just becomes a system of free fermions. So your Gibbs free energy is just the Gibbs free energy of free fermions. If you take c going to 0, then the Cauchy kernel becomes the delta function. Okay? And that allows you to solve this equation quite easily. Right? So you just get the epsilon of k that is given in the notes, t log of e to the k squared minus mu over t minus 1. Okay, and that just gives you the case of free bosons. Okay, so if you substitute this back into the expression for the Gibbs free energy, you will find that instead of minus t integral, it becomes plus t integral of log of 1 minus. Okay, like you would for bosons. Okay, so everything is kind of consistent. We've been able to interpolate completely between free bosons and free fermions by the deep vinegar construction field, at least as far as the thermodynamics are concerned. Okay? Yeah, I guess that covers what I wanted to tell you today. I'll open the floor for questions. Maybe one last comment is that the formalism of the thermodynamic beta ansatz is, for all practical purposes, identical for all integrable models that we know. You do it the same way, it's just you might have to glorify it in particular ways. Here we had only one type of, if you want, rapidity. In spin chains, for example, you have an infinite number of allowable types of rapidities. However, the thermodynamic beta ansatz equations, they take the same form, just that you have an epsilon for each of the possible types of particles, and they're all coupled to each other. But still the idea is the same. So what you learn here is completely transferable for other integrable models.
Thank you.